So we are beginning our exciting mammal run today with Johanna Eckert, who is currently a postdoc here at UCLA. And she will be giving a talk called The Evolutionary Roots of Intuitive Statistics. Johanna is currently at UCLA, as I mentioned, but she is beginning a postdoc at Max Planck with Daniel Hown on the early cognitive development in great apes. So please join me in welcoming our speaker.
Yeah, thank you all for coming today. After having participated in the Beck series for a couple of months as a part of the audience, it's now really an honor for me to be here and be able to present my work to you. So as Erica said, I'm currently working here on a project with her, and I will briefly give you an overview about this current project at the end of this talk, but the main part of the talk today will be about my PhD work in which I investigated the evolutionary roots of intuitive statistics. So at first glance, this term intuitive statistics may seem a bit contradictory to some of you, because how can something as complex as statistical reasoning be intuitive at all? And I always like to answer this question by giving a brief practical example. So what you see here are two letters informing you that the paper you recently submitted to Science was either accepted or rejected. Okay? Now you can make your personal decision which of the two letters you would be happier to receive. Once you've made this decision, you can look at this here. These are two bowls filled with acceptance and rejection letters. Okay, now let's imagine we had these two bowls here and you can witness the editorial decision process. So I close my eyes and draw randomly one item out of one of the two bowls and you get whatever it is. Which bowl would you want me to draw from? Easy, right? I think all of you would want me to draw from the bowl on the right side because you intuitively know that it is more likely to get an acceptance letter as a sample out of this population of items compared to this one. So this was easy. Now look at this here. Here it gets a bit more tricky, right? Because here absolute and relative frequencies of acceptance letters are disentangled. So even though there are absolutely more acceptance letters in the population on the left side, if you pay attention to the proportions, then you see it's still more likely to get an acceptance letter as a randomly drawn sample out of the population on the right side. And this is intuitive statistics. So this term refers to our intuitive capacity to draw inferences from populations of items or events to randomly drawn samples, and also vice versa, from sample to population. And this capacity is actually of fundamental importance in our daily lives because it enables us to use proportional information to make predictions about the outcome of events and thereby to make decisions and judgments under uncertainty. At the same time, it also allows us to draw general conclusions from limited sample observations and therefore probably plays a crucial role in inductive reasoning and learning. Despite the ubiquity of situations presumably requiring statistical inference in our daily life, for quite a long time, psychological research accumulated evidence showing that humans are actually surprisingly bad in statistical reasoning tasks. So for example, it was shown that statistical abilities develop quite late in human ontogeny, and that even in adulthood, statistical abilities remain fragile and error-prone, and are mainly a product of simple heuristics and perceptual biases. Also, it was suggested that humans are only capable of true statistical inference in very limited contexts, namely only when they can rely on experienced frequencies of past events. However, in the last decade or so, new nonverbal measures were established, and intriguingly, in contrasting all these previous predictions, it could be shown that even pre-verbal infants have a sense for intuitive statistics. So for example, when infants were presented with a population of items and they witnessed the sampling process, they were able to draw conclusions about the resulting sample, just like you in the beginning of this talk. And this also worked in the other direction. When presented with a sample, infants drew conclusions about the likely composition of the population the sample came from. And importantly, infants also considered the sampling process and used different types of information to judge whether a sampling event was truly random or not. So together, these studies showed that intuitive statistics is already present in the first year of life, which clearly suggests that neither language nor formal education are necessary prerequisites for this kind of ability. And this then in turn raised an interesting question, namely, are we dealing with a uniquely human ability, perhaps accounting for our unprecedented cognitive flexibility, or is it rather part of our evolutionary heritage and we may therefore share it with other animals, especially with our closest living relatives, the great apes? We already know that great apes share with humans some fundamental similarities in basic numerical cognition. So for example, great apes can represent and discriminate between different absolute quantities, and they can even perform basic arithmetic operations on these representations. However, clearly intuitive statistics is much more than the capacity to represent and discriminate absolute quantities. It rather is the capacity to represent and discriminate proportions of quantities and to form probabilistic expectations based on these representations. So the question is, do these basic numerical abilities extend to intuitive statistical abilities? By the time I started my PhD, there was only a single study directly investigating this question. And in the study, Macaque et al. Presented individuals of 4 great ape species at the Leipzig Zoo with a task very similar to the one I conducted with you in the beginning of this talk. So what happened is that apes saw 2 populations of food items which differed in the proportion of preferred food, in this case peanuts, and non-preferred food, in this case pieces of carrots. And the apes saw these 2 populations and then could choose from which of the 2 populations they wanted to receive a randomly drawn sample. And what was found is that the apes indeed were able to choose the sample coming from the proportion-wise more favorable population, and they even did so in conditions in which absolute and relative frequencies of peanuts were disentangled. So this study showed that just like human infants, also great apes can reason from population to sample, giving a first hint that also great apes might be intuitive statisticians. And the aim of my PhD then was to build on these first findings and shed more light on the evolutionary roots of intuitive statistics. So I tried to answer 3 distinct but related research questions regarding the generality and flexibility of intuitive statistics in great apes, their cognitive structure and limits, and the integration with other types of information. So regarding the generality and flexibility, I wanted to find out whether apes can not only reason from population to sample, but also the other way around, from sample to population. And I'm not going to present the study today, but in short, what I found is that to some extent the apes were able to reason from sample to population. However, in this study, we were not able to fully rule out that they did use a quantity-related heuristic. Regarding the cognitive structure and limits, I investigated the signatures of intuitive statistics, both in chimpanzees and in humans. And regarding the integration with other types of information, I investigated whether chimpanzees consider an experimenter's mental states when drawing statistical inferences. So today I'm going to present study 2 and study 3, and I will begin with the study on the signatures of intuitive statistics. Yeah, so what are the cognitive structure and limits of intuitive statistics? How do great apes and also humans actually represent statistical information? One thing that might be quite obvious is that it probably has to do something with representing quantities. And actually we already know quite a bit about how humans and also non-human animals represent quantities. And I'd like to illustrate that with another practical example. So if I'd ask you, which number is larger, 26 or 27? Each of you could tell me it's 27, just as easy as if I would ask you to compare 1 and 2. And this is one of the great advantages of our symbolic number system, because if you look at the respective quantities, then suddenly this task gets way more difficult. Right? Suddenly you cannot discriminate 26 from 27 anymore without counting, even though the absolute difference between these 2 quantities and these 2 quantities is the same. So is this because it's just too many dots? No, because look at this here, this is 26 and 52. Now it gets easier again. And this is because it's not about the absolute difference between the quantities or the absolute number of items within each set. It's about the relative difference or the ratio between them. And this is called Libas Law. So the ratio between 2 quantities determines how easy they are to be discriminated. And this is a characteristic signature of the cognitive mechanism enabling this kind of capacity. And this mechanism is called the analog magnitude system or the approximate number system. And signatures of this system have been found in a wide variety of different quantity-related tasks and also in a wide variety of different species. So for example, here's a study by Cantland and Brennan in which they presented rhesus macaques and humans with the exact same quantity discrimination task. And you can see that even though the humans here in green are slightly better than the monkeys, both showed this clear ratio-dependent performance in accordance with Libas Law, suggesting that the analog magnitude system is involved here in both species. Now, if we assume that intuitive statistics is based on the capacity to discriminate quantities, and in particular proportions of quantities, we would expect to find similar signatures in a task requiring inferences from population to sample. And this is what I wanted to investigate in this study. So to answer this question, I went to Ngamba Island Chimpanzee Sanctuary in Uganda, where I tested 24 chimpanzees who were all completely naive to this kind of task. And all the individuals there were born in the wild and orphaned at a young age before they were brought to the sanctuary, where they now live in this semi-natural environment. By contrast, the chimpanzees and the other apes tested in the previous study, they were all born and housed in the zoo. So conducting this study in a sanctuary now also enabled us to have a nice comparison between these two quite distinct populations of chimpanzees. So to explore what the signatures of intuitive statistics are, I presented the apes with a task very similar to the one of the Rakoczy et al. Study. So again, they could choose from which of two populations of food they wanted to receive a randomly drawn sample. But this time, to test for the signatures, I systematically varied the magnitude of difference between the two populations, or in other words, the ratio between the two ratios. So this here would be an example for a relatively high magnitude of difference or a high ratio of ratios. This would be a relatively low magnitude of difference or low ratio of ratios. And I don't want to go into too much detail. Basically, all you need to know is that I tested 8 different ratio of ratios ranging from 1, which would be the same proportions in both populations, up to 16, which would be the highest magnitude of difference, and which was also the ratio of ratio that had been used in the previous study. And importantly, in all of these conditions, I disentangled absolute and relative frequencies of peanuts to make sure that the apes were really reasoning about proportions. So for example, here in ratio of ratio 6, you can see the more favorable population contained 28 peanuts and 7 pieces of carrots, and the less favorable population contained double as many peanuts, but even more pieces of carrots. However, there's also an alternative way for how chimps could succeed in this study without necessarily relying on statistical inference. And maybe this becomes a bit apparent when you look at the picture. I hope you can see that a bit. So theoretically, it's possible that the chimps succeed not necessarily relying on statistical inference, but simply by avoiding the sample coming from the population with absolutely more pieces of carrots. And so to address this alternative way to solve the task, I added a control condition which I called the carrot avoidance control, in which the more favorable population contained 4 times as many carrot pieces than the other one. And the ratio of ratio in this condition was kept at 16. Each condition was tested in a single session, and the order of conditions was randomized for each subject. Now to give you a better impression how that looked like, so this is ratio of ratio number 8, so intermediate difficulty, I would say. You can see first I present the populations to the chimp, and then I close my eyes and draw one item out of each of the 2 populations, and the chimp can choose between the 2 hidden samples. And you've seen I crossed my arms in this trial. I did this in half of the trials to make sure that the chimps were really picking one of the hidden samples and not just pointing towards one of the populations. So briefly to the statistical analysis, all the data you will see today was analyzed using GLMMs, which allowed us to control for various factors such as trial number, session number, subject age, and so on. If you would like to see the individual models, I'm happy to show them to you later. Okay, so here are the results. This is the proportion of trials in which chimps were correct in the different ratio of ratio conditions. And this is a bubble plot, so the size of the dots represents the number of individuals performing on the same level. Okay, now I would like to guide you through this graph step by step. So first, you can have a look at this here. This is the ratio of ratio 16 condition. Here the chimps were correct in around 70% of trials, which is pretty much comparable to what has been found in the previous Rakoczy et al. Study. So this condition can be seen as a nice replication of these previous findings, and it shows that intuitive statistics, or at least reasoning from population to sample, seems to be a common capacity in chimpanzees, regardless of their housing and rearing background. Next, you can have a look at this here. This is the carrot avoidance control, where the more favorable population contained 4 times as many carrot pieces than the other one, while the ratio of ratio was still 16. And you can see that here the chimps performed even significantly better than in the ratio of ratio 16 condition, which shows that in this study they did not seem to use such an avoidance heuristic. Also important is the ratio of ratio 1 condition, where both populations contained the same proportion of preferred to non-preferred food, only in different absolute quantities. And here the chimps did exactly what we expected them to do. They performed at chance level. So this further shows that they did not use an absolute quantity heuristic in this study. And then most importantly, we found a highly significant correlation between the ratio of ratios and the performance of the chimpanzees in accordance with Libas Law, suggesting that the analog magnitude system is involved in this kind of reasoning. Yeah, when we obtained these findings, we started wondering what this would look like if we presented humans with the same task. So we developed a computerized version of the same task and tested human adults. And also for them, we found a highly significant correlation between the ratio of ratios and the proportion of correct choices. Again, if you would like to see the human data or hear more about them, I'm happy to show you some extra slides later. Okay, so what we could take home from this study was that intuitive statistics shows very similar signatures as absolute quantity discrimination, both in humans and in chimpanzees, which suggests that the analog magnitude system is involved in both species. Also, we could show that intuitive statistics is a common capacity in chimpanzees and not restricted to one experimentally highly experienced population. And this was the first study on intuitive statistics in great apes, which comprehensively ruled out absolute quantity heuristics, both regarding preferred food items, non-preferred food items, and absolute total amount. So coming back to the 3 goals, so far we've seen that great apes can reason from population to sample, to some extent also vice versa, and the cognitive structure seems to be very similar as for absolute quantity discrimination, both in chimps and in humans. So now we are left with the last goal, in which I investigated the integration with other types of information. So one important characteristic of human intuitive statistics is that this capacity is not cognitively isolated. Instead, humans are able to integrate various types of information, for example, to judge whether a sampling event is random or not. And this is already the case in pre-verbal infants. So infants know, for example, that physical constraints can influence sampling events when one type of objects just can physically not be drawn in the same way as the other, for example, because it is too far away from the opening of the container. Also, infants know that psychological constraints can influence sampling events. For example, when an experimenter has a preference for one type of object and visual access to the population while sampling, then infants expect the sample to reflect these preferences regardless of the population's composition. So for the apes so far in all the studies, sampling was always apparently random. So the question was whether chimps also know that under some circumstances sampling can be non-random, and whether they can use information about mental states to judge whether this is the case. So to test this, I again went to Ngamba Island, where I tested 21 individuals in 3 different experiments. And the setup was again quite similar as before, but this time I had 2 experimenters, namely my colleague Johanna and myself, and throughout each experiment, each of us would always sample out of just one of the 2 buckets. Okay, so the first experiment consisted of 2 phases, a demonstration phase and a test phase. And in the demonstration phase, the chimps experienced that the 2 experimenters were not acting neutrally, but had specific biases or preferences for one type of object. And so what happened is that in alternating order, my colleague Johanna and I would look into our bucket, search for 3 seconds, and just hand over a piece of food to the ape. And importantly, we always sampled the minority type of food. So in this case, Johanna would sample peanuts out of the mostly carrot population, thereby indicating a preference for sampling peanuts, so the same preference as the ape has, whereas I would always sample carrot pieces out of the mostly peanut population, thereby indicating the opposite preference. And we did this 10 times in a row and repeated it the next day, and then on the next 2 days we tested the individuals in the test phase, in which they could then choose from which experimenter or which population they wanted to receive a sample. And we had 2 different test conditions, and the only difference between them was that in the visual access test, we looked into the buckets while sampling, whereas in the no visual access test, we sampled blindly. And each condition was tested in a single session, and of course the order of conditions was counterbalanced between subjects. So here you can see a quick video of the visual access test. So first we would present our populations to the chimps. And then simultaneously we would look into the bucket, search for 3 seconds, and offer the chimp a chance between the 2 hidden samples. And the no visual access test started out the same way. But then to emphasize our lack of visual access, I would place a screen in between us and the buckets. We would turn away and then simultaneously sample blindly 1 item each. Okay, so before I show you the results of these 2 test conditions, I briefly want to introduce you to a second experiment, which we conducted just to have like a baseline comparison. And this experiment was conducted half a year later with the same individuals, the same experimenters, but new types of food. And this time the chimps did not get any demonstration phase beforehand. So the idea was that they should have no reason to assume that the experimenters were somehow biased. And also both experimenters always sampled blindly. And here are the results for this second experiment. What you see here is the proportion of choice or a proportion of trials in which the chimps chose the sample from the more favorable population. And you can see that in this last experiment, the chimps clearly preferred the sample coming from the more favorable population in around 90% of trials. Okay, so this is how chimps would choose normally in this task setup when they had no reason to assume that the experimenters were somehow biased. However, in experiment 1, they knew that the experimenters were biased. When these biased experimenters sampled from the populations, but they sampled blindly, the results looked like this. So now the choice was not as clear anymore, but still in around 59% of trials, chimpanzees chose the sample coming from the more favorable population. Now, if the same experimenter sampled from the same population, but this time looked into the bucket while sampling, the results looked like this. So now, clearly and statistically significantly, the chimps preferred the sample coming from the experimenter who had the same preference as they themselves, regardless of the proportional composition of the population. So these 2 experiments showed that without any prior information, chimpanzees assumed random sampling and expected the sample to reflect the proportions within the population. However, if they had reason to assume that the experimenters were biased, then their choices also reflected these biases. And the severity of this influence was dependent on whether or not the experimenters had visual access to the population. However, there's also an alternative explanation that could explain these findings. So in experiment 1, during the demonstration phase, we differentially rewarded the chimps, right? So maybe it's possible that they simply associated, for example, Shona with peanuts and me with carrots, and that's why they chose Shona's sample in this condition and not mine. And that they chose differently in the no visual access test could then be explained by the fact that here the setup slightly changed. We had the screen in between us and the buckets, so maybe that's why they fell back to the intuitive statistics strategy. So to address this alternative explanation, we conducted a third experiment in which we did non-differentially reward the chimps. So again, we tested the same individuals with the same experimenters by new types of food, and this time in the demonstration phase, both of us would always sample the preferred item, in this case grapes. And the crucial difference between us was that Shona would always sample grapes out of the mostly grape population, which is not very surprising, but I would always sample grapes out of the mostly broccoli population, which is quite surprising because it violates statistical likelihoods. So the idea was that during this demonstration phase, chimps should conclude that I, but not Shona, have a preference for sampling grapes. And then in the subsequent test phase, both experimenters sampled from identical 50-50 populations, and the chimps could choose from whom they wanted to receive a sample. And the results looked like this. So this is the proportion of trials in which chimps chose the sample coming from the experimenter who expressed this preference by violating statistical likelihoods. And you can see that in around 65% of trials, which is significantly above chance level, chimpanzees preferred the sample coming from this particular experimenter. And the results looked like this from the first trial onwards. So this shows that even when prevented from associative learning, chimpanzees intuitively used a violation of statistical likelihoods to infer the biases of the experimenters. So what we could take home from this study was that chimpanzees do make random sampling assumptions, and they notice when these random sampling assumptions are violated by biased experimenters. And in such cases, they are able to override the statistical inference accordingly. Also, we could show that chimps used statistical information, in particular a violation of statistical likelihoods, in order to infer the preferences and behavior of others. So coming back to the three goals, what we've seen so far is that great apes can reason from population to sample, to some extent also vice versa. And the cognitive foundation of this ability seems to be the same as for absolute quantity discrimination, both in humans and in chimpanzees. And moreover, we found that chimpanzees used information from the social domain to judge whether an event was random or not. So if you now look at this triangle down here, you may realize that this looks pretty much the same as the one I showed you for human infants at the beginning of this talk. So these findings suggest that great apes and humans share the capacity of intuitive statistics. Yeah, so what do these results really tell us? What do they imply? I think they imply quite a bit. So first of all, they give us important insights into the cognitive architecture of great apes. In the beginning of this talk, I told you that there are various theories according to which humans mainly rely on general purpose heuristics to make statistical inferences, and that they are only capable of true statistical inference in very limited contexts, namely when they can rely on experienced frequencies of past events. By contrast, these results now show that even great apes can reason statistically about events they've never experienced before, and these inferences do not seem to be a product of heuristics or perceptual biases. And this finding that they did consider information from the social domain when drawing statistical inferences might be a first hint that this inference mechanism may be domain general. And if that was truly the case, it would suggest that great apes, like human infants, possess a very powerful tool, probably allowing them to rapidly acquire knowledge about their environment and also to predict the outcome of events in a variety of different contexts. So future research should try to shed more light on this potential domain general mechanism and try to see whether chimps also consider other types of information, such as physical information, and also in different task setups in different contexts. A second implication of my findings is that intuitive statistics seems to be an evolutionary, rather ancient capacity, which was probably already there in the last common ancestor of humans and other great apes. By now there are also 2 studies using the same task setup to test 2 species of monkeys, namely Capuchin monkeys and long-tailed macaques. And so far these studies did not find unambiguous evidence for competences comparable to those of great apes and humans. So this might be a first hint that this capacity developed later in primate evolution. However, there are also other studies using different task setups, and 2 very recent studies found that one gray parrot and some pigeons were at least sensitive to probabilistic information. So I think in order to really be able to reconstruct the evolutionary roots of intuitive statistics, it will be important to use the same task setup to test a wide range of different species. And if we would then find comparable abilities in other species, this again would give us insights into both which cognitive prerequisites are necessary for this ability, and also which ecological pressures may have led to the evolution of these capacities. And then a last implication of my findings is that together with the findings on human infants, they clearly suggest that statistical reasoning is something that is deeply rooted in the human mind in form of a non-symbolic approximate mechanism. Yeah, and you have seen that the signatures of this mechanism are following Libas Law, so the output is really not exact but only approximate. So this means that this intuitive mechanism may not necessarily be involved when we are dealing with more explicit symbolic statistical information. So one important question for future research will be to investigate what exactly is this relationship between this intuitive non-symbolic approximate mechanism and more formal symbolic statistical reasoning. Yeah, so as I promised in the beginning of this talk, we'll now move on to a topic that I'm currently working on together with Erica. And this project goes beyond statistics in a way that we are interested in what apes actually understand about expectations, and in particular about the expectations of others. And the background of this topic is the following. So for human infants, it was shown that already in the first year of life, infants seem to play with the expectations of their parents in form of playful teasing behavior. And there are several observational studies which identified 3 common types of playful teasing in preverbal infants, namely offer withdrawal of objects or the self, provocative non-compliance, and disrupting others' activities. And the most common form, and I think the most interesting one, is this first one, offer withdrawal of objects or the self, which you can also see in this picture sequence down here. So what usually happens is that the infant offers an object, for example a toy, to the parent, and as soon as the parent tries to reach for it, the infant withdraws the offer and starts laughing. And typically this is repeated a couple of times, and all while the infant is closely looking at the parent and smiling or laughing whenever the withdrawal event happens. So it seems as if infants would here actively create expectations in the parent, namely that the toy will be transferred, to then playfully disrupt his expectations again. And the expressed surprise of the parent then seems to be a source of amusement for the infant. So this behavior is really interesting, first of all, because it might involve some early theory of mind abilities, which allow the infant to some extent to understand and manipulate the expectations of the parent. And at the same time, it's also interesting because it might constitute an early form of joking behavior, and therefore might give us interesting insights into the ontogenetic origins of humor. So during my PhD, I showed that great apes can form rational expectations about events. And now the question is whether they are also aware of others' expectations, and whether they, like human infants, may like to playfully play with these expectations. So our first approach to this topic was to try and find out whether we find similar types of playful teasing behavior in great apes as have been described in infants. And to that end, we conducted an extensive literature review. And this review showed that even though there is no study yet directly investigating playful teasing behavior in great apes, This type of behavior has been mentioned several times in the literature for different great ape species. And intriguingly, the type of teasing we currently have the most convincing evidence for is the offer-withdrawal of objects or the self. And here you can see a picture sequence of how that can look like in great apes. So there's a male orang here on the left side of the mesh, and he brings a stick into reach of this female on the right side. And as soon as she tries to reach for the stick, he withdraws the stick again. Only to soon after offer it again, this time close to her face. She tries to bite in it, but before she can do that, he withdraws the stick again. And the sequence went on for quite a while, for several minutes, and at some point there was also a role reversal where then the female brought a stick herself and did the same with the male. So this behavior seemed really playful and not aggressive at all. Yeah, so these preliminary findings suggest that great apes may playfully tease others in similar ways as human infants do. And this opens up quite interesting research questions. So first of all, what do apes really understand about these expectations of the other? Do they anticipate that somebody else's expectations will be violated? And second, do they enjoy watching such expectation violations in similar way as human infants do? I tried to address these two research questions in a study in Japan, and I just returned around a week ago. So in Japan, I conducted a study in collaboration with Fumihiro Kano at the Kumamoto Chimpanzee Sanctuary. And I want to briefly show you what I've done without going into too much detail, but the basic design of the study is very straightforward. So first, the chimpanzee subject itself was playfully surprised, and then it could watch how somebody else was surprised in the same way. And we had different surprising scenarios, and I show you one of them here. This is the surprising food taste scenario. So the chimps at Kumamoto Sanctuary are used to getting grape juice out of different containers, like for example out of small bottles, and you can see that Hatsuka here immediately opens the bottle and drinks the juice, and they like this quite a lot. And now the surprise was that Kano would now bring a different container, namely a little plastic bag, which was also filled with juice, but it was not normal juice. It was mixed with a lot of citric acid, so it was really, really sour. And the chimp drank it without hesitation, and I hope you could see that, immediately spit it out and was a bit confused. Okay, and so after the chimps made this experience themselves, they then could watch how a familiar human, this is Sato here, made the same experience. So he was also handed the sour juice, and here Hatsuka knew that it was not a normal juice in there, and she could watch. Yes, so and what we wanted to see is whether the apes anticipate that that Sato's expectations will be violated here, and to that end we used looking time, and more specifically we compared, or we looked at the 10 seconds right before the expectation violation happened and coded whether and how long the chimp was looking at the scene, and then we compared it to a comparable scene of a control condition which was identical apart from the fact that here the human stooge received the normal grape juice. So here no expectation violation happened. So this was the first question I wanted to answer, and the second was that I wanted to see whether apes reacted emotionally, perhaps even mirthful, to seeing such an expectation violation. And to do so I used thermal imaging. Thermal imaging makes use of the fact that the skin temperature changes in response to experiencing emotions. And in great apes and also in humans, this is especially apparent in the nasal area. So the nasal skin temperature drops when we experience emotionally arousing events. And so also here I compared the nasal temperature in a condition in which the expectation violation happened to a condition in which it did not happen. Yes, and as I said, I just returned recently, so unfortunately today I cannot show you the results yet, but I hope this will change soon, and I'm already looking forward to present these results in the near future. Yes, so to come to an end of this talk, what I hope you take home from this is that great apes are intuitive statisticians. They can form rational expectations about events based on an understanding between the populations and samples. And we gathered first preliminary evidence that great apes may also like to play with others' expectations in form of playful teasing behavior. And with this, I would like to thank all the people and institutions involved in this research, and of course you for coming here today and listening. Thank you.
Thank you. It's really fascinating stuff. I have two questions for the two parts of your talk. The first is maybe asking you to clarify your conceptual conclusions in the first half. And that's that you stated that you thought that this was evidence of a domain general mechanism. And of course, in arguments about domain generality and domain specificity, a lot hinges on what the definition is, and that proponents of either position can always escape to sort of what appears to be changing the definition, moving the goalposts. But it strikes me that if by domain generality you mean that humans and chimpanzees can reason statistically about a variety of different contents, then I agree with you. But if by domain generality you mean that the capacity for this statistical reasoning is not derived from or the product of a mechanism dedicated to that task, that is statistical reasoning, but rather is just a product of some general information processing, then it seems to me that you don't have evidence of that. Right? So could you clarify what you mean by
so first of all, I hope I didn't say I have evidence for a domain general mechanism. I said this may be a first hint that we are dealing with something that is not restricted to one situation. I think I'm more on the side of they can use this mechanism for different types of contents, different types of contexts. So, for example, I assume that they also use this mechanism to make social decisions, for example, to pick the most reliable collaborator, or to infer habits of other individuals and to avoid conflicts, things like this. So this is what I meant with we might have a domain general mechanism.
Yeah, I wouldn't, so again, try not to be pedantic here, but to be clear, I wouldn't take that as evidence of domain generality, right? The fact that an adaptation can produce output that has implications for other task domains does not mean that it is not a specific adaptation.
Yeah,
right?
You're right.
So, bipedality is an adaptation. There are a lot of things that you can do if you walk on two legs, but the fact that you can do those things by virtue of walking on two legs doesn't speak to whether that is a discrete adaptation.
Yeah.
And so, like you cited Tubi and Cosmides in one of your early slides, right? If we take classic work there, like cheater detection, right? There are many domains in which cooperation or free riding can occur, right? The fact that there is a, the position that there is a dedicated mechanism for detecting free riding across those different tasks suggests that that is not a domain general capacity, right? But rather there is a thing that is free rider detection. And then once you've done that, you make decisions about who you interact with and so on. So it sounds like maybe we're on the same page, but we just have some different ways of carving up the conceptual space. So my second question is about this intriguing project on teasing, maybe you could call it. And that's how we understand the anticipation that leads to or is part of the positive playful motivation. So dogs do exactly the same thing of offering something and then withdrawing it, right? And they do it in playful, friendly interactions with known conspecifics, right? A skeptic might argue that what the dog is doing is trying to initiate a chase sequence or a fight sequence, a play-fight sequence, right? So it isn't the withdrawal that is the goal in itself. It's what happens when you withdraw, as it were, right? So how do we know that that's not what the orangutan or the chimpanzee or the baby is doing?
I think right now we don't know. So right now we're really just collecting examples that could be similar type of playful teasing compared to infants. I think for infants it's... So I'm just thinking about whether you could use the same argument for human infants. And I think for them it's more likely that they really enjoy the withdrawal moment because that's when they start laughing, and it seems that this is what they aimed for. For the apes, what we could do is look at what happens after. And I think, so in this example with the orang, it was unlikely that a chasing would occur because they were separated by a mesh.
Maybe there's some struggle over the stick or something like that.
But I think it was not that because it repeatedly happened. I think the male repeated it around 10 times. And the female first wasn't interested in engaging in this game, and then he started exaggerating his movements, like moving the stick in front of her face until she made the grasp again, and then he withdrew it. So I think it's my impression that it was what he was aiming for, that she would somehow react to the stick. But at the moment we don't know.
Can I just jump into this? I do think, I think it's a really good question, Dan, and it's something that we've been trying to grapple with a little bit, but I do think that you see two different behaviors in apes, and one of them, can I just demonstrate it? No, but one of them is the I'm gonna hit you and then I'm gonna run away. And you get that juvenile, chimps do that a lot, right? Where it's okay, you come up and I yank on you or I smack you and then I quickly run away. And that seems, and I do think that's very clearly chase initiating. But that's very different from a lot of these object teasing is often I'm sort of, very relaxed, and I'm like, how are we gonna do that? Right? And I feel like you get this sort of very different embodiment where there isn't a, I as the object extender and withdrawer, I'm not moving my body away to initiate to invite a follow. And they often happen between an adult and a juvenile where, I think that the adult is sort of entertaining the juvenile. So I do think, I feel like we haven't figured out the right way to kind of differentiate, quantitatively differentiate these situations. But I do think that there's something that's very in alignment with the kinds of chase initiating sequences you see in dogs. And I think that this object teasing does seem to be at least qualitatively different.
So I think dogs do both,
okay.
right? Which is don't you want this? Don't you want this? Now chase me and try and get it, right? Mm-hmm. But there's also don't you want this? Okay, now we're gonna kind of go, we're just gonna mouth over this object, and no one's running away, right? It reminds me of things that I've heard Susan say about these Capuchin games where, try and get my, finger out of your mouth, or my, your finger out of my mouth, or a piece of my tail, or whatever it is, right? Which is, they're not aggressively wrestling, but it isn't just, if, and Clark's here, he can speak to this, if one thinks that surprise is a key component of some aspect of humor, right? It's not clear that there's really a lot of surprise here. Like by the 10th time that the female orang has experienced that, right?
Yeah.
There's no surprise there,
Yeah.
right? Which makes me think it's something more like the kind of Capuchin game, right? And dogs, as I said, they do both of those, right? Which is the chase me thing, but also the, try and get it, don't you wish you had it, kind of, you know. And I'm not really trying to keep it away from you, it's just the engagement there. And that doesn't seem like it engages, like it involves surprise at all. But this is all anecdote, I have no systematic observation.
I think it's an interesting. This will be my last thing I'll say, and then I'll shut up because it's your talk. But I think the question of is it surprise is really interesting, because I completely agree when you think about surprise in human adults and the sort of expectation violation that's involved. It is very different, right? When you do something 7 times in a row, it's not surprising. But I do think that it's very similar to the kind of sort of formalized surprise that human infants engage in, where they do the same thing over and over and over and over, and it often involves this kind of initiation of a behavior with then something that violates the way that typical routine is played out, and that can be repeated multiple times in a row. And so I think the question of whether you call it a true surprise, maybe we shouldn't use that word, but I think that what we're seeing, at least hints of in the apes, does seem like it's pretty similar to that kind of sequence of behavior in humans, right?
Yeah.
Going back to the first set of experiments, I'm surprised you're surprised because, any animal, bird, mammal that, comes out of its hole has to decide where the best place to go for the food. So they're not randomly wandering around. They've got to have some kind of picture in their head of the odds of the nuts being ready here this time of year, this location, this place. So that seems to me it would be a very broad-based ability to conjure up odds in your daily foraging especially, or your interactions with others. So I was curious to know more details about in what way the 2 monkey studies failed to find what you found with the apes and the babies.
Briefly to the first point you said, I think there are different ways how an animal can cope with uncertainty. I think many animals, or most animals, have some innate decision rules, and I think these decision rules can, for some animals, be updated by learned information. For example, about this type of fruit is likely to be ripe this time of the year. But I think this is not necessarily the same as the intuitive statistic that I have shown, because this is something that the apes have never experienced before. They see the situation and intuitively can draw inferences about what's going to happen. And I think that this is qualitatively different from coping with uncertainty that you have somehow experienced before. Yeah. And then the second part, the Capuchin monkey study and the long-tailed macaque study. So they were, for the Capuchin monkeys, they were quite successful in the study actually. They succeeded in most of the conditions. However, they failed in something equivalent to the carrot avoidance control. So when the more favorable population contained more unpreferred food items than the other one, then they failed. So they performed at chance level. So right now we cannot rule out that this is how they solve this task all the time during the study. And for the long-tailed macaques, they only succeeded in conditions in which absolute and relative frequencies of preferred food items were confounded. So they seem to use the mental shortcut, I go for the population where more peanuts are, basically regardless of the proportional composition of the population. But there was one individual who was successful, 9 of them were not. So I think maybe it's too early to conclude that they are not able to do this.
So they weren't taking the person who was going to be feeding it to them into account. They were looking at what was in the field.
Now, so they had 2 populations of food items with different proportions of preferred to non-preferred food. And there was one experimenter sampling out of the 2 buckets simultaneously like this, and they could choose between the 2 hidden samples. Yeah, and they chose the more favorable population only when it contained absolutely more preferred food items than the other one. Yeah, but by now there are also 2 studies using different task setups in monkeys. For example, one with rhesus macaques where they used looking time, and they found some evidence that they might be able to solve this task when they are not explicitly asked to decide, but only basically look at a surprising outcome versus a non-surprising outcome. There they were successful. So yeah, I think maybe this task setup is also not the right way to test monkeys for several reasons. Yeah. Oh, yeah.
Hi.
Hey.
Thanks for those are really great experiments and experimental data. I also had a question. Well, one small comment and a question about the domain specificity issue. So it seems like maybe this relates to what you're saying with all of it, that I don't know if you call it an interaction with theory of mind, but right, in the chimpanzees, they're able to take into account others' preferences and also what others can see. And that interacting with statistical reasoning, it seems to me that could be evidence of some domain specificity, right? That there's a domain-specific interaction, or at least there's an interaction with another domain-specific ability that maybe not all species would have, because maybe a non-social, you can imagine there could be non-social species that could still do intuitive statistics without taking into account others' perspective or something. Right? So this could be an interesting feature of apes or something. My question was, on domain specificity, I was thinking about Weber's law and the idea that it's a signature of intuitive statistics, because as you know, it's also a signature of almost anything quantitative in cognition, right? Like, if I put 2 weights in your hand, and one of them is 1 pound and the other is 2 pounds, it's a lot easier to tell the difference than if one's 25 pounds and one's 26 pounds. But that's not a statistical inference, right?
Yeah.
So I guess what I'm wondering is, it almost seems like Weber's law is more domain general than intuitive statistics. So in what sense is it a signature of intuitive statistics?
So I think all these different, like weight, like light intensity, duration, all of this shows the same signatures. And there's still some debate going on whether there is cognitive mechanisms strictly responsible for numerical information, or whether it is rather something more domain general, which deals with all kinds of magnitudes. And that is also why I call this mechanism analog magnitude system and not the approximate number system. I would say yes. Basically all animals that have ever been tested have shown these signatures of an analog magnitude system. Not all species that have been tested are able or capable of intuitive statistics. So definitely there is some level on top of this basic mechanism. I think this study that I showed shows that the analog magnitude system is somehow involved on a basic level, but what's coming on top, so far we don't know.
Can I just follow up?
Yeah.
Do you think the difference is, it sounds like the one difference that can distinguish it from other perceptual cases of Weber's law is that there's something like units that are that it's like cognition over multiple units? Is that?
With units?
Well, because you have peanuts, you've got pieces of carrots, either like, sometimes people do things in event parsing, and then sometimes it's item parsing, but like, is that what would maybe distinguish it as a statistical inference?
Maybe so. I think so. What we don't know is whether the apes, or I think it's likely that the apes did not see the individual pieces of food, but rather like in a continuous quantity, which they could estimate the size of. I think so. The difference between absolute quantity discrimination obviously is that you have to represent proportions of quantities, and in this case 2 different proportions, and then you have to form this probabilistic expectation. So this is obviously different, but we just don't know which mechanism is doing this. So there is some neurobiological evidence that shows that representing proportions of quantities is happening in the same areas of the brain as representing quantities. And there is also some evidence in humans that also these areas are active in probabilistic reasoning tasks. So probably there's a strong connection, but yeah, we definitely need more research to show that.
So I was wondering whether in the studies where they're taking the psychological preferences or constraints into account, is there any kind of transfer that goes on from, basically, do they make inferences about, this person or this being is like me in some ways, and so then I prefer them in other contexts. So rather than just, I'm going to request peanuts from them and give them the opportunity, do I, assume they're going to make a better cooperation partner, or do I spend more time near them, or, do you get this kind of transfer, or if no one knows, would you expect that there be any sort of...
It's an interesting question that we haven't thought about yet. Of course, it's likely that if they see that a person could give me peanuts, but she does give me peanuts, could give me peanuts but gives me pieces of carrots, of course it could be that they somehow think that this person is not so nice, so I should not, if I have the choice in a not related task, not interact with this person, rather with the other person. But could definitely happen. But so this demonstration phase was pretty short, so it happened 10 times in a row, and we repeated it the next day, so 20 times in total, I think, is not that much for a chimp to learn such a general rule, I would say. But yes, we don't know. So we could do something like this and give them the choice to interact with one of the experimenters afterwards to see if they generalize this nice giving peanuts to some other task. Yeah. Would be interesting, definitely. Yeah.
Along the same lines, I mean, this is not really about your talk, but just in general, that was reminding me of a question I've often had. With a population like the Leipzig population, where these apes are basically professional test takers. I mean, they've got decades of experience in solving cognitive tasks. And I've wondered whether anyone's ever done a meta-analysis of how their experiences with certain people, certain test givers, or certain kinds of tasks influences their performance in subsequent tasks. It seems like it would be a really interesting thing to know.
Surprisingly not. I know that some people had planned to do something like this, but so far, to my knowledge, they haven't. So there is all this data of 15 years, I think. So it would be really interesting to see that.
Yeah, I think so. It would tell us a lot about how they psych us out, or what kind of theory of human mind they might have.
Great talk. It's really fun to see all this work taking shape and to see what you've demonstrated already. And I'm not a specialist by any means in any of this stuff, so I was wondering if you could explain where you see the boundaries between heuristics and intuitive statistics. Like, what is the formal definition of those terms that allows us to separate those two things as explanations for behavior?
So in general, heuristics are mental shortcuts that leave out a part of the relevant information and usually lead to good enough results in daily scenarios. But since they leave out parts of the information, they can lead to systematic biases and errors under some circumstances. And I think the easiest way to distinguish between a result that came that is the result of a heuristic and the result that is the result of an intuitive statistics mechanism is to directly test for these most likely heuristics that we know are present in humans. So there's really a lot of research on heuristics and on probabilistic reasoning in humans, and there are many different types of heuristics. And so for example, the representative heuristic is one that is very common or very well known. So usually people, when they make probabilistic reasoning, or when they try to reason from population to sample or vice versa, what happens quite often is that they judge the likelihood that a sample originated from a population by the way that the sample resembles the population somehow. So it's like it's a mental shortcut. You see, this looks like similar like this population, so probably it stemmed from this one. But it disregards a couple of important features. So for example, a typical error that happens because of this heuristic is the gambler's fallacy. So that, for example, when you have a random process and like a roulette wheel, and you've had red a couple of times, and many people think that now black is due because it's a random sequence that should be somehow, so the sample, the outcome should somehow represent the two possibilities equally. So this is something that happens quite often, and I think if we know that these heuristics exist in humans, then it would be interesting to create situations in which these heuristics are not successful, and then see if the chimps or the apes still succeed. Does that answer your question?
Yeah, it does. So does having intuitive statistics, does that category mean they are not using heuristics, or is it some sort of statement about what kinds of heuristics are used, or how heuristics are combined, or
So,
what is the?
I would say, yeah, intuitive statistics is something that excludes heuristics. But of course, if we have results that look like somebody is reasoning, somebody is using intuitive statistical abilities, then these may also be achieved by a heuristic in the same way. We just may not be able to discriminate them. So, for example, for the monkeys, for example, it seemed in the first experiments as if they would really do intuitive statistics, as if they would use the proportional composition of the population to reason about the sample. But in the end, what they did, they used a mental shortcut, namely they simply focused on the absolute number of non-preferred food items and then picked the sample coming from the bucket with less non-preferred food items. So, yeah, intuitive statistics is something else than heuristics, but sometimes it's not easy to discriminate the two.
I'm trying to think of natural scenarios where these animals might strongly need this capability. Like this, and it sounded like you thought that this came from foraging and then maybe became part of social life. But if I'm thinking about foraging, if I'm an ape trying to pick which tree to go to, it seems to me that my estimate of the absolute quantity of my preferred food is more relevant than if there happens to also be some unpreferred food lying around. Are there obvious natural scenarios, or especially foraging scenarios, where this is especially relevant?
Of course, I try to think of examples. So one example that I could imagine is that, let's say you have two trees, fruiting trees, and you look at, to judge which one you should climb on, you look at the fruits lying on the ground, and maybe one tree has a couple of ripe fruits, but most of them are not ripe. The other one has mostly ripe fruits, maybe fewer than the other one, but now I forgot which, but you get what I mean. So I think this could be an example of that in the foraging context.
So it's something where you have to engage, like where you have to pay a fixed cost. Like I have to choose to climb a tree, and I don't have all the information that's up there.
I think so, yeah. Or where you have to be fast to decide. You don't want to waste time. You want to be the first one. But yes, and I don't know if this capacity evolved in the context of foraging or in the context of something else. So it could be both ways. And I think it is quite useful if you have this capacity to discriminate proportions of things also outside of the feeding context, like for example in the social context. Yeah.
Just to add on to that too, I think often watching Capuchins, they'll have a fistful, like a twig full of some ripe and unripe, and they may have to do more processing work to get just the ripe out of the combination of ripe and unripe, either spitting things out more or picking through things that are in their hand more. So I think that's an application.
I was wondering if you could just talk a little bit more about one of your findings that I thought was really intriguing, which was, I'm not going to be able to quote you correctly, but you were basically, I thought you were implying that they were, apes were sensitive to when others' preferences violated the statistical distribution of items in the world, right? And so I wondered if you could sort of talk a little bit about that, maybe thinking about how that would apply to social situations, or are apes attending to individuals whose preferences, sort of contradict things, not the natural order, you know what I mean? Where where they're salient in some particular way, like you're preferring something that is less, is less frequent. Does that, is that something where you see them paying more attention to those individuals, or are there ways in which that that sensitivity might play out in making social decisions as well?
So I'm not sure I'm really getting what you exactly mean.
Like if Larry is friends with, an individual that no one else is friends with, is that something where you're going to pay attention to that friendship because there's something in that individual that is...
For sure, I would say, because this is actually how you learn new things, right? By focusing your attention to things you didn't know of. I think that's also the principle of looking time studies, for example, in human infants, that they look more at events that they didn't expect to happen because they are more interesting and therefore have a greater potential to lead to new knowledge that you didn't have before. Regarding the preferences in apes, so you think that, or you're aiming at whether the chimps pay more attention if, for example, I draw peanuts out of mostly carrot population. The chimps pay more attention to this compared to when I do the opposite.
Yeah, I guess just getting back to Dan's question about domain generality, I'm wondering whether the intuitive statistics, phenomenon could be part of, or sort of one possible, selective pressure that has resulted in sensitivity to intuitive statistics could be, the possible benefit of recognizing when others' behavior violates.
Okay. Yeah.
Not preferences, but when others' behavior sort of violates the random chance.
Yes. Yeah, I definitely agree on that. I think that's quite likely that this is, and I don't know if it has evolved in this context, but it's definitely a benefit of intuitive statistics that you notice when something is not as it is usually, that you can shift your attention to the situation and selectively learn from it. This definitely.
So, any other questions? All right, well, please join me in thanking our speakers.